DC biasing of bipolar junction transistors part 1. Fixed bias circuits. Transistor biasing is important in order to make a transistor operate correctly, and in discrete circuits resistors are often used. The point at which we bias the transistor is called the quiescent point or Q point, and this is the point on the output characteristic that shows the DC collector emitter voltage VCE and the collector current IC with no input signal applied. So if we look at the characteristic curves for this particular NPN transistor and we choose to some point in the active region to bias our transistor, then having chosen our Q point, we can see that we need to bias our transistor so that we have 10 volts between the collector and the emitter when a current of 7 milliamps is flowing in the collector. Okay, so here's our NPN transistor. We're going to need 7 milliamps collector current when the collector emitter voltage is 10 volts and when a base current of 0.2 milliamps is flowing. I didn't actually mention that, but that dot or the Q point actually laid on the curve that it was sitting on was the curve corresponding to 0.2 milliamps base current. Now the fixed bias circuit uses a very simple arrangement of two resistors. One I'm going to call R1 and the other's RC. The RC is in the collector of the circuit, and we need to remember that when we put that this transistor is being biased by a power supply, which effectively is a battery between the upper rail, the 16 volt rail in this case, and earth, and that we're going to require these currents to be, the resistors to be such as to allow these particular currents to flow into the base and collector respectively when the collector emitter voltage is 10 volts. Right, so to tackle the problem of trying to calculate these resistors, it's best to remove or ignore one side of the circuit. So I'm ignoring this side of the circuit, the base side of the circuit, and I'm just looking at the collector. And you can see that essentially I've got a 16 volt supply being connected through the resistor RC and through the transistor. Now, using Kirchhoff's law, we know that 16 volts must be equal to the voltage dropped across the resistor RC plus the voltage dropped between the collector and the emitter. So I can immediately write down an equation: IC times RC, that's from Ohm's law. We know the collector current times the collector resistor must be gives the voltage dropped across the collector resistor, so that's ICRC plus 10 equals 16. Now when you rearrange this, take the 10 over the equal sign, becomes ICRC equals 6. Substitute the collector current of 0.007. See how I've changed the milliamps to amps before I've plugged it into the equation, and then divide both sides by the collector current, and you see we obtain a value of RC 857 ohms. Let's now look at the base side of the circuit. So I'm going to ignore this side of the circuit and again remind myself that there is a voltage of 16 volts sitting between the top of R1 and ground, and that the voltage dropped across R1 plus the voltage drop between the base and the emitter this time must add up to 16 volts. Now the base emitter voltage is typically 0.6 volts, so I'm going to plug in 0.6 volts for the base emitter voltage. I'm going to plug in 0.0002 for my base current, because that's 0.2 milliamps expressed in amps, and that's equal to 16. When I subtract 0.6 from both sides, I end up with 0.0002 times R1 is 15.4 or dividing both sides by the 0.0002, I end up with 77,000 ohms or 77 k ohms. So I've calculated my two bias resistors for this using this fixed bias circuit. What are the advantages of a fixed bias circuit arrangement? Well, it's simple, as we've just seen, and of course we can easily change. If we change these values, it's easy to shift the Q point, the operating point, anywhere in the active region. There's only two resistors required, but there are certain disadvantages. One of them is that the collector current doesn't tend to remain constant with variations in temperature or power supply. Therefore, we say that the operating point or the Q point, the quiescent point, is unstable. Changes in the base emitter voltage will easily change. Small changes in the base emitter voltage will change the base current and thus cause the emitter current and the collector currents to change, and this will in turn alter the gain of the stage. So the gain tends to fluctuate quite a bit with this arrangement. When the transistor, if you want to replace this transistor with another one, even if it's the same number, the same numbers provided by the same manufacturer, the values of beta vary a lot. So you're going to get, just by plugging in a new transistor, you're going to change your operating point quite a bit. So again, it's not very stable as a circuit. And for small signals, not power transistors, with relatively high values of beta, this configuration is prone to a thing called thermal runaway, which we'll talk about in future lectures. Now, due to the above, then this fixed bias arrangement is rarely used in linear circuits. And the linear circuits, by the way, are those circuits in which the transistor acts as a current source. However, you can use this fixed bias arrangement when you wish to use transistors as switches.